All right, take two. Sorry about the technical difficulties earlier. So let's get going. So we're talking about uh, general problems in separation of variables, okay? And in particular today, we'd like to focus on convergence of generalized Fourier series. And what I mean by that is, not just sums of trigonometric functions, sine and cosine, but any Fourier series, any complete orthogonal set that you can construct L2 functions from in the L2 norm. So last time, let's just recap, depending on when you're watching this. Remember that we looked at linear operators that look like this, right? L is ddx of p times du dx plus q of x u is equal to lambda r of x u. Okay, we call this a Sturm-Liouville problem. And the domain that we'll work with is the open interval from A to B. Okay. What can we say about L? Well, we can say that L is symmetric if the boundary conditions are symmetric. For example, they could be Dirichlet, right? They could be Neumann. They could be periodic, okay? And I think also they can be, Dirichlet, periodic, and Neumann. Okay, so, and if that's the case, right, then we have that P times U V prime minus U prime V conjugate evaluated at x equals A to B, right, is going to be 0 in that case, okay? So that's what we're going for. What does symmetrics exactly mean? Okay, well, given the L2 inner product, right, UV, then we have that the inner product of LU with V is equal to the inner product of U with LV, okay? And just to define the L2 inner product, right, it's U of X, V conjugate of X, integrated against one another, integrated from A to B, okay? What do we get by knowing this? Well, the eigenvalue problem that we can construct using L, okay, has all real, okay, eigenvalues. Moreover, the eigenfunctions are orthogonal to each other, okay? Is it a complete set? Well, we haven't said that yet, okay? We also recall different notions of convergence, right? What are these? Well, there's three main ones that we talked about. Pointwise convergence, okay? Uniform convergence, which is stronger, and L2 convergence, okay? And just to sum up, we have pointwise convergence if fk goes to f of x, right? We have uniform convergence, which is stronger if the sequence, the maps of the norm, the infinity norm, of the difference in a sequence goes to 0, that some sequence of functions goes to f. And L2 convergence just means that the L2 norm goes to 0. And that ends up being, the weakest form, but it's sort of the easiest to deal with, okay? And we also said that C2 functions are dense in L2, right? If I have an L2 defined function, then I have close by a C2 function. So if I have L2 convergence, that means my function is converging to an L2 function, and so it's going to be a reasonably good approximation to the C2 function that I'm interested in. Okay, so that's kind of what we talked about last time. Where are we going with this? Well, we'd like to say some things that are a bit firmer about this eigenvalue problem, right? And we'd like to maybe say something about completeness, and then we'd like to say something about the series that we can construct from our eigenfunctions, okay? Hello. So let's say, I said series, and Siri thought that I was talking to her. Okay. So let's say we have L, okay, and boundary conditions symmetric. Then it turns out the following things are true, okay? And these are going to be stronger conditions than we talked about before, and I'll just refer you to a proof in a supplemental text, Strauss, which I've put on Canvas, okay? So there exists an infinite set of eigenvalues such that the one closest to 0 is simple, okay? And then I have a bunch of eigenvalues bigger than that, right? So each eigenvalue, okay, has a finite number of multiples, okay? But it could have, more than one. Lambda 1 is simple. Lambda n goes to infinity, okay, as n goes to infinity. Good to know. The other thing is that eigenfunctions Vn of x, okay, can be chosen to form a complete orthogonal set. And they're orthogonal with respect to the L2 norm, okay? Why is that good? Well, because it means we can make any function that we like by linear superposition of these functions. And it's not going to be hard to extract those coefficients due to the orthogonality that we have, okay? And the proof of this, okay, I will refer you to chapter 11 of Strauss's Intro to PDE book, okay? Now, given these eigenfunctions Vn, okay, of our linear operator, what we can say now is that any f that's in L2 can be represented, okay, as follows. F of x is equal to n equals 1 up to infinity, where the coefficients are going to be the inner product of f with Vn times Vn, okay? And let's call this equation star, okay? And this brings us to a theorem now. So this, right, what is this? This is like just a generalized Fourier series, right? Those Vn's, yeah, they could be trigonometric functions, but they may be something else, right? Solutions to our Sturm-Liouville problem, right?